This lecture explores leveraging pre-trained convolutional neural networks, also known as convnets, for image classification. Using pre-trained models is a powerful technique to speed up training and improve performance, particularly when you have limited data. We will look at two main approaches: feature extraction and fine-tuning. First, let's discuss feature extraction. This method uses the convolutional base of a pre-trained network to pull out meaningful features from new images. These features are then fed into a new, smaller classifier that you train on your specific data set. The idea is that the pre-trained convnet has already learned a hierarchy of features from a large data set like ImageNet, and these learned features are general enough to be useful for various image tasks. In the first code example, we set up the environment and load a sample dataset, MNIST. Although it's noted that for better results with convnets on images, a dataset like CIFAR10 or custom image data would be more appropriate, the code preprocesses the MNIST data, resizing and converting the grayscale images to 3 channels to match the expected input shape of the VGG16 model. It then loads the VGG16 model without its top classification layer using weights pre-trained on ImageNet. The code proceeds to extract features from the resized training and testing data using the loaded VGG16 convolutional base. After extracting features, it flattens them and builds a simple sequential model with a flattened layer and 2 dense layers as a new classifier. This new model is compiled with an atom optimizer and categorical cross-entropy loss, and then trained on the extracted features. Finally, the model is evaluated on the test features to report the loss and accuracy. Next, we delve into fine-tuning. Fine-tuning is a more advanced technique where we not only add a new classifier on top of the pre-trained convolutional base, but also unfreeze and train some of the layers in the convolutional base along with the new classifier on the new data. This allows the pre-trained model to adapt its learned features more specifically to your dataset. It is generally recommended to unfreeze only the top layers of the convolutional base because these layers have learned more specific features compared to the lower layers, which have learned more general ones. The second code example demonstrates fine-tuning. It starts with the same data loading and pre-processing steps as the feature extraction example. It then loads the VGG16 model without the top classification layer. A custom classifier consisting of a flattened layer and 2 dense layers is added on top of the VGG16 base. Initially, the convolutional base is frozen by setting the trainable attribute of its layers to false. The combined model is compiled with an atom optimizer and categorical cross-entropy loss and trained for a few epochs, primarily to train the newly added top layers. After this initial training phase, some layers of the convolutional base are unfrozen. The code shows unfreezing layers starting from index 15 onwards in the VGG16 model. The model is then recompiled with a very low learning rate using the atom optimizer. This is crucial for fine-tuning to avoid drastically changing the pre-trained weights. The model is then trained for more epochs on the resized data in this fine-tuning stage, allowing the unfrozen convolutional layers and the custom classifier to be jointly trained. Finally, the fine-tuned model is evaluated on the test data. In conclusion, using pre-trained convnets through feature extraction or fine-tuning are effective strategies for image classification, especially when working with limited data. Feature extraction is simpler and faster, while fine-tuning can potentially lead to better performance by allowing the pre-trained features to adapt to the new dataset. The choice between these two techniques depends on the size of your dataset and how similar your new task is to the original task the pre-trained model was trained on. It is always a good practice to experiment with different pre-trained models, the number of layers to unfreeze during fine-tuning, and various hyperparameters to achieve the best results for your specific image classification problem.